Welcome to the second lecture on deductive and inductive arguments. In this lecture, we're going to learn our second skill, which is how to classify arguments into the two major types, deductive or inductive. Our first skill was to learn the parts of an argument and how to determine the conclusion of an argument. Of course, we have to be able to do that in order to proceed, and now we're going to master the second step. We have to learn to distinguish between deductive and inductive arguments because eventually we want to be able to evaluate arguments to determine if they're good or bad, and deductive arguments are evaluated in a somewhat different way and through a different set of standards than inductive arguments are. So in order to evaluate them properly, we first have to classify them properly. Okay, so in this lecture, we're going to learn our second skill, which is classification of arguments into those that are deductive versus those that are inductive. An argument must be one or the other, deductive or inductive. It cannot be both. There's a sharp line between these two types of arguments. So as I said, this is our second skill. Our first skill was learning how to analyze arguments into their component parts and to accurately identify the conclusion of an argument and then separate out the premises so we could see what the argument is about. Obviously, of course, you can't evaluate an argument if you don't know what it's about, and so that's an important initial step. Now today we take our second step and learn our second skill, which is classification. The reason why this is important is because deductive arguments are evaluated in a slightly different way from inductive arguments, and therefore we have to learn to classify them correctly before we can then go on to evaluate them properly. So let's go on to see what the difference is between these two types of arguments, and then we'll learn about some typical inductive and deductive arguments along the way, and that'll help to make our job a little bit easier. Here we go. Many of you have probably heard of deductive arguments and inductive arguments, and you probably learned this distinction sometime along the way during your academic career. Very often, for example, this distinction is taught in high school English composition classes when you're learning how to write an argumentative essay. It's good to know the different types of arguments that exist. However, in most cases, when this distinction between deduction and induction is taught, especially when it's not taught by philosophy professors, it's taught in an incorrect way. Very often we're presented with some notion that deduction involves going from general propositions to draw specific instances or specific conclusions, whereas induction is the opposite, where we go from specific observations to draw a general conclusion, something like that. Unfortunately, those are not correct definitions because, well, for various reasons, and I won't go into the details. However, you're going to have to take my word for it. They just simply don't work. They're not adequate as ways of defining the distinction between deduction and induction, so we have to do it in a slightly different way. And here's how we're going to discuss this. The basic distinction between these two types of arguments is going to rest solely on the strength of the inference in the argument. Now, what does that mean? Well, an argument contains an inference. That is, from the premises, we infer or draw the conclusion. Now, how rigorously, how strongly that conclusion follows determines what kind of argument we're dealing with. For example, if I say, okay, here are 2 apples, and I give you 2 more apples, it is necessarily the case that you have 4 apples. That is a very strong inference. It has to be the case because 2 plus 2 is 4. It would be weird if I were to say, if I give you 2 apples and then I give you 2 more apples, you probably have 4 apples. That should sound weird to you because it is weird. When we're talking about mathematical reasoning, for example, we're dealing with a very strong inference where the idea of something necessarily being the case follows. That's the idea of an inference being very strong, whereas a somewhat weaker inference would be something like, oh, I see some clouds in the sky. It's probably going to rain today. When we talk about probability, the inference is less strong. It's less certain. And so where an argument falls on this scale between necessity and probability is going to determine whether or not it's deductive or inductive. And let's go into this a little bit more, and I'll give you some examples. All right, so first let's talk about deductive arguments. This is an argument where a conclusion is claimed to necessarily follow from the premises that are given. In other words, starting with the evidence or the information in the premises, we draw an inference that it is claimed must be the case. And what we will learn down the road is when that is true, when the premises necessarily do lead to the conclusion, that's going to be a valid deductive argument, but let's not get into that. Now let's just learn about the nature of deductive arguments. So let's explore this idea of something necessarily following. I think it's a fairly intuitive relationship if you have an example. So for example, let's say that today is Wednesday, just to pick a day. So given that today is Wednesday, is it necessarily the case that tomorrow is Thursday? Think about that. Imagine today were Wednesday. If it were Wednesday, could tomorrow be any other day than Thursday? No, it couldn't. It has to be Thursday. So it is necessarily the case that tomorrow is Thursday if today is Wednesday. In other words, given that premise that today is Wednesday, it necessarily follows that tomorrow is Thursday because Thursday follows Wednesday. And that's an intuitive kind of sense of this notion of necessity, of necessarily being the case. Now let's contrast that with induction and inductive arguments, and you'll see that they are two utterly separate categories of reasoning. Inductive reasoning does not involve necessity. Inductive reasoning involves probability, drawing a conclusion that something is probably the case based on some evidence. So this is a fairly broad notion that I think we're pretty familiar with because we use this kind of reasoning all the time. We use deduction also, but we also use induction probably more frequently in our daily lives. So for example, if you're driving to school and there's a lot of traffic, let's say, and you've got 10 minutes to get to class and there's all kinds of traffic on the freeway. Well, based on that evidence that there's traffic on the freeway and you've got 10 minutes to get to school, you can infer that you will probably be late for class. Now, that's not necessarily the case. The traffic could instantly open up and you could drive really fast and you might get to school on time, but that's probably not going to happen. So when we're reasoning about probability, we are reasoning inductively, not about what is necessarily the case, but what is likely to occur based on certain information. So like my previous example, if you look at the sky and there's lots of dark clouds gathering and the temperature is dropping, that is evidence that it is reasonably likely that it is going to rain, that a storm is coming. It's not necessarily the case. Those clouds might blow on through, but it's probably the case because those dark clouds and that drop in temperature are signs or indicators of the likelihood of a storm. So this is the major difference. Probability is inductive, necessity is deductive. Let's compare the two in a little bit more detail. Before we look at typical types of deductive arguments and typical types of inductive arguments, let's do one last little comparison here where we have them side by side and we can try to determine more clearly the distinction. So as we know, deductive arguments are distinguished by the idea that the argument claims, given a certain set of information or the premises of the argument, the conclusion necessarily follows. And that just means that the argument is saying, starting with this information, the conclusion has to be the case. Like in my example with the days of the week. If you start with the idea that today is Wednesday, the conclusion that tomorrow is Thursday has to be the case because it's impossible for it to be any other day. So that's that idea of necessity. And we're going to look at a variety of different types of arguments that are typically deductive in this way, where they make a claim that something has to be the case based on certain evidence. Now, in contrast, inductive arguments do not make claims of necessity. They make claims of probability or likelihood. So the idea is that In an inductive argument, we are extrapolating, we are speculating that something is likely the case based on the information in the premises. Very often, inductive reasoning makes a claim about the future, for example. And the evidence for this claim about the future is what has happened in the past. Now, we know that if something has happened in the past very, very frequently, very commonly, or for a very long time, it's more likely to happen again. Whereas if something is very rare or has never happened in the past, then it's less likely to occur. But in neither case is the idea of necessity involved. Just because something has happened a lot in the past doesn't mean it's necessarily going to happen in the future. And just because something has never happened in the past doesn't mean it's never going to happen in the future either. So we're dealing with probability. For example, the formerly San Diego Chargers, the Los Angeles Chargers, haven't won a Super Bowl ever in 45 years of their history. So it is very likely that they will not win the Super Bowl this year either. Does that mean it is necessarily the case that they will not win the Super Bowl? No, it just means it's unlikely. It could happen, but it is improbable. So when we are speculating about the future, making a prediction, let's say, we are reasoning inductively because we cannot be certain about our conclusion, but we can be reasonably likely and reasonably assured that it's going to be the case. All right, so let's look at some typical kinds of deductive arguments. Naturally, the best way to recognize a deductive argument is to grasp the conceptual relationship that a deductive argument has between premises and conclusion, that is, that it's a relationship of necessity. However, if you can simply recognize that an argument is a mathematical argument or an argument based on definition, you have a shortcut. You're going to know automatically that it's a deductive argument. So it just facilitates your classification. And of course, we want to classify arguments right because we want to be able to evaluate them according to the proper means of evaluating deductive versus inductive arguments. So let's look at some typical deductive arguments. And here you have a list. These are classes of deductive arguments you see here. We're going to go through these 6 types of arguments. Some of them have some terminology you may not be familiar with, like hypothetical syllogisms, for example. Don't worry, the terminology isn't really that complicated, and I'll explain it when we get to that particular type of argument. So let's look one by one at these typical types of deductive arguments to help us to be able to recognize them when we see them. So the first type of deductive argument will be one we've already seen. It's one where the conclusion necessarily follows from the premises. And we have as an example here our previous example. If we start with the information that today is Tuesday, the conclusion, therefore tomorrow must be Wednesday, follows necessarily because Wednesday follows Tuesday. So here you have a relationship where if you start with that premise, you have to accept the conclusion. There's no way to deny it, so therefore it is necessarily the case. If you have 31 people in a room, it necessarily follows you have an odd number of people in the room. That just necessarily follows from the information that you're given. Now, arguments like this are relatively infrequent, but it's nice to know because it helps to reinforce this notion of necessarily following that is essential to a deductive argument. However, we will rarely encounter these in everyday life, but we do encounter them. So let's go on now to look at some other examples of deductive arguments. Various forms of mathematics, arithmetic, geometry, algebra, basically are collections of deductive reasoning. And it's fairly easy to see with a few examples why mathematical arguments are deductive. If you think of an equation as kind of a deductive argument, it's easy to see that if you have 3 ounces of a solution and you add that to 5 ounces of solution in a flask, 3 plus 5 must be 8. It has to be, and this is necessarily the case, not merely probably the case, right? If you have a square in geometry, imagine a square in geometry, and you draw a line from one corner to the opposite corner, well, then you're going to bisect that square, and necessarily you will have 2 triangles. It's not a matter of probability, it has to be the case. So when you see mathematical arguments, your default position should be that's going to be a deductive argument. Now, there is one significant exception to this, and this would be statistics. Arguments that depend on statistical inferences, polls, statistical claims of probability that something is likely to a certain percentage. For example, statistical arguments will be inductive because they don't lead to necessary conclusions, they lead to probable conclusions. But all other mathematics treat it as a deductive argument. Any argument where the conclusion follows necessarily because it is a definition of the key term in the premises is going to be an argument based on definition, and it's going to be deductive. Let's look at the example here on the slide. Bob just graduated medical school with a specialty in nephrology, therefore he is an expert in the physiology and diseases of the kidneys. Now here, the conclusion that Bob is an expert in diseases of the kidneys necessarily follows because that's what it means to have a specialty in nephrology. So the conclusion could not be anything else, and therefore it necessarily follows. If we say that Bob is a philanthropist, therefore he's generous and gives money to causes to help humanity, that necessarily follows also because that's just what it means to be a philanthropist. And so therefore, when you have an argument based on definition, the conclusion's necessarily going to follow because it is just extrapolating the meaning of a key term in the premises. Now let's look at the first of our three syllogistic arguments. The term syllogism is an ancient term that just refers to a deductive argument pattern. Some patterns are very, very common, and they're so common that they have been named for the distinctive feature that they have. A hypothetical syllogism has the distinctive feature of being a deductive argument that contains a conditional statement. Now, a conditional statement is nothing very complicated. It's just an if-then statement. If you study, then you'll pass the class. That is an example of a conditional statement. If you get a good night's sleep, then you'll feel better in the morning. That's another conditional statement. So a hypothetical syllogism is a deductive argument that contains at least one conditional statement. When you see a conditional statement in an argument, your thought should be instantly, that's a deductive argument, and you have classified it correctly. Here's an example of a hypothetical syllogism here below. If you were a diligent student, then you would pass the class, but you didn't pass the class, therefore you are not a diligent student. This is an example of a hypothetical syllogism, and we're going to learn in our next set of exercises and lectures to how to evaluate an argument that looks like this. But for now, the important thing is simply to recognize that because that first statement has a conditional statement as its basis, if you were a diligent student, then you would pass the class. That's your clue that this is a deductive argument. A disjunctive syllogism is another deductive argument pattern. It's different than the hypothetical syllogism because instead of having a conditional or an if-then statement, the key feature of a disjunctive syllogism is it contains a disjunctive statement, and that's just basically an either-or statement. As you can see down below here, this is an example of a disjunctive syllogism because the first statement or premise, either George Washington or Jean-Paul Sartre was an existentialist philosopher, is the marker of this kind of syllogistic argument. So either George Washington or Jean-Paul Sartre was an existentialist philosopher. George Washington was not an existentialist philosopher, therefore Jean-Paul Sartre was. Now, the reason why this is a deductive argument, of course, is that given those two premises, the first premise gives you an alternative, either George or Jean is an existentialist, and the second premise says, well, but George is not. So therefore, the conclusion that Jean-Paul Sartre was, given those premises, is the only possible outcome. So therefore, this conclusion follows with necessity, and therefore we have a typical kind of deductive argument. The last category of syllogistic arguments that we're going to look at briefly are the categorical syllogisms. This is an enormous area in classical logic. And it's the evaluation of categorical syllogisms can get very, very complicated, but the basic idea is pretty straightforward. A categorical syllogism is one where categories of things are related to each other, like all dogs relating to the category of all mammals, for example. So here we're talking about categories rather than individuals, okay? And so as you can see, a categorical argument has three categorical propositions in which some category term appears. And these are terms like all, some, or no. All right? So down below we have a categorical argument. All mammals are animals. All dogs are mammals. Now, if you put those two ideas together, since all dogs are mammals and all mammals are animals, as the premises tell us, therefore the conclusion, therefore all dogs are animals, necessarily follows. So this is a very broad category, and no pun intended, and categorical syllogisms are somewhat tricky to deal with, but I will try to provide you some simplified rules down the road to help you to deal effectively with these without getting into the deep forest of evaluating categorical arguments. The key point here is to just simply recognize at this point that this is a deductive argument and leave it at that. And we'll work on the other stuff later on. So that completes our brief survey of typical kinds of deductive arguments. Again, just designed to help you more effectively easily spot deductive arguments and distinguish them from inductive arguments. Now we're going to shift gears and look at some typical kinds of inductive arguments. This is a pretty big category of argument types that are probably going to be familiar to you once I give you some examples. We often encounter these in everyday life very frequently. We have arguments based on signs, statistical arguments. Remember, I'd mentioned that math is generally deductive, but statistical arguments are inductive. We have predictions, historical arguments, inductive generalizations, analogies, arguments based on authority, and causal reasoning. These are all very different from each other, but they all share a common core, and that is they create arguments. They are types of arguments where evidence is given for a conclusion, but the conclusion can only follow with probability. So let's go through these and see what they entail, and this will help us more effectively be able to spot inductive arguments when we see them. The first type of inductive argument we're going to look at is an argument based on signs. Now, a sign can be just a literal sign, like a stop sign, for example, or an exit sign. And from reading that sign, we infer that the information contained in the sign is probably correct. For example, if the sign at the back of the movie theater says exit, well, you can infer that there's probably an exit back there. Notice I said probably. It's not necessarily the case that there's an exit there. Maybe the building was recently renovated and the exit was boarded up, but they didn't take the sign down for some reason. Maybe they forgot. So even though the sign says there's an exit there, it doesn't necessarily have to be the case, but it probably is the case. And that's an important distinction which makes an argument based on signs inductive. Now, a sign can also be used more extensively to refer to things that are not literally signs, like a street sign or an exit sign. Anything that really can be meaningfully interpreted. If you go to the supermarket, for example, and you're going down the vegetable aisle and you see a can in front of you and the label on the can says corn, well, that can probably contains corn. And that label can be interpreted as a sign as well. Again, it doesn't necessarily contain corn. They might have put the wrong label on stuff, and maybe it has beans in it or something, but it probably does have corn. So that sign, that label, is reliable. We could also interpret as a sign anything that can be meaningfully interpreted. For example, the sky getting very dark and ominous as clouds are building up can be interpreted as a natural sign that a storm will occur. And this is an example I've talked about previously. It's probably going to be a storm given those markers or signs, but not necessarily the case. So an argument based on signs, whether literal or more extensively interpreted, always going to be an inductive argument. Statistics is the one category of mathematics where we draw probable conclusions, and that makes statistical arguments by their very nature inductive. Very often we are drawing a conclusion based on a limited sample of a larger population. And so the idea is, well, what's true of this limited sample is probably going to be true of the larger population as well. And so therefore we draw that conclusion. However, the conclusion that we're drawing based on that sample can only be probable and never necessarily the case. For example, if we take a poll and we determine that 90% of the incoming freshmen at Cal State San Marcos will ultimately graduate, and we know that John is an incoming freshman at Cal State San Marcos, well, we can reasonably conclude that he will graduate, but only with a very high degree of probability. Since 90% of the students do graduate and John is an incoming student, he will probably graduate, but not necessarily. And therefore you can see that when we draw a conclusion based on statistics, we can only draw a conclusion to a degree of probability. And percentages are kind of the metric of that degree of probability. So if something is 45% likely, well, that's not very likely. If something is 90% likely, then it's very likely. So you could see that statistical arguments fall into a scale of likelihood or probability. That's what contributes to making them inductive by their very nature. When you make a prediction, you may be very, very confident that what you are predicting is going to happen. However, oftentimes that's not the case. Even when we feel the most confident, sometimes we predict something that doesn't occur. That prediction may be likely, but it's never absolutely certain. And so therefore, since the future is not certain, an argument based on a prediction is going to be only probable to a certain degree and therefore inductive. For example, Big Bear Lake's roads did not require chains last year after Memorial Day for the summer season, so this year I don't have to bring snow chains on my summer trip to Big Bear Lake. Here we're predicting that the weather is going to be mild and there won't be any snow on the roads. Now, that's probably likely based on past weather patterns, but notice it's not necessarily the case. Even as late as May or June, a freaky storm might come in and drop a bunch of snow on the roads, and you will probably wish you had your snow chains because your prediction turned out to be incorrect. So even though a prediction may be very likely, we may have a high degree of confidence in it, nevertheless, predictions are never going to be absolutely necessary. The outcome of the future will always be to a certain degree opaque to us, and even our best efforts to predict what's going to happen often go wrong. You might be surprised to note that historical arguments about events that happened in the past, are also inductive, for similar reasons that predictions are inductive. When we make a historical argument, we are always basing our argument on information about the past, but this information about the past is always going to be incomplete. We might have documentation, we might have eyewitness accounts of events, but these are always subject to interpretation, and they may turn out to be incorrect. Just because someone in the past said something happened at a certain date, let's say, they might have been incorrect, and therefore when we're drawing a conclusion based on their testimony, we are drawing a conclusion that isn't necessarily the case. Here's an example of a historical argument. Thomas Jefferson was extremely shy and uncomfortable speaking in public, tended to focus obsessively on his studies, and sang or hummed to himself incessantly. It is therefore likely that if he lived in the modern world, he would have been diagnosed as being on the autism spectrum. Now, this is an argument about the personality, the characteristics of a historical figure who lived hundreds of years ago. Now, we're basing our conclusion on information about Thomas Jefferson, what people said about him, which may be more or less correct, but even so, this conclusion, even if it is reliable, can only be reliable to a certain percentage and isn't necessarily the case. The picture we have of Thomas Jefferson might be completely false or false in certain areas, and therefore we can't say anything with any certainty about the past, but we can conclude things to a reasonable degree of likelihood or certainty, at least in terms of probability. It gets worse the farther back you go in time, of course. Conclusions about, say, the cause of death of King Tut, for example, which happened thousands of years ago, are always going to be extremely speculative and based on historical reconstructions. So the further back you go, the more sketchy the record gets, and therefore the more cautious we should be about any conclusions. So whenever anybody says something with absolute confidence about the past, you should be skeptical about that, because we always need to be a little bit cautious about these kinds of claims. An inductive generalization, or just a generalization, is where we draw a general conclusion based on specific individual experiences. Now, we're going to learn down the road that you have to be careful about this, but if you have a large number of experiences and they are normal kinds of cases, then generalization can be a perfectly fine, reliable form of inductive reasoning. For example, John owns a pit bull that is friendly and loyal. Bill owns a pit bull that is friendly and loyal. Jane owns a pit bull that is friendly and loyal. So here we have three individual cases of pit bull owners that have dogs with certain characteristics. From these three individual cases, we generalize and we conclude, therefore, all or most pit bulls are friendly and loyal. Now, this is a general claim about all pit bulls based on three experiences. It's a fairly limited kind of example, but the point is that this is an illustration of generalizing. If you generalize from normal cases and you don't take your generalization too far or make it too extreme, then it's a perfectly reliable form of inference. However, the key here is that any generalization is only going to lead to a conclusion that is probable or likely and never necessary. So we have to be cautious with generalizing, and we have to generalize from a sufficiently robust sample of things that are the normal cases. When you draw an analogy, you're arguing that something is similar to something else. In an argument from analogy, you draw a conclusion about something because the thing you are drawing the conclusion about is similar to some other thing. And so you argue, well, because these two things are similar, what's true of the one thing is probably going to be true of the other. For example, if your friend John owns a Toyota Corolla that's very reliable and you're interested in buying a car that has similar properties, it would be reasonable to conclude, well, maybe I should buy a Corolla as well, because my car will be similar to John's and therefore I will have similar experiences and that the car will be very reliable. When the two things you are comparing are in fact very similar, this is a perfectly legitimate form of reasoning. However, you do have to be cautious and realize that just because two things are similar, it doesn't mean that what's true of one is necessarily true of the other. And a lot of this is going to depend on how similar the two things are. So keep in mind, arguments from analogy are based on similarity. The more similar two things are, the more likely it is that what is true of one is true of the other, but not ever necessarily the case. An argument from authority is an argument where we draw a conclusion based on a person's expert information or knowledge, or because of the opinion of some authoritative source of information. We do this all the time, and it is perfectly rational, and you do it yourself. For example, if you wake up and you have a really, really bad toothache, well, you're not going to talk to your friends and ask for a diagnosis. You're going to go to a dentist, because the dentist has authoritative knowledge about teeth and therefore is more likely than your friends to give you an accurate diagnosis. Notice the authority of the dentist can lead to a likely conclusion that you have a cavity or something else wrong with your teeth, but even experts can get it wrong. However, a qualified authority will give us a conclusion that is likely to be the case. Here's an example. Economist Phil Bellum, who predicted the last economic crash, says that another economic crisis is on the horizon. Therefore, I'm going to buy gold to protect the value of my savings. Here, the person is drawing a conclusion about a certain course of action based on the opinion of a relevant expert, an economist, about an upcoming or pending economic crisis. Now, just because this expert says this crisis is going to happen doesn't mean it necessarily will, but I would respect the opinion of an expert on this matter more than I would some layman or some uninformed person. We rely on the information of experts or authoritative sources of information for the very reason that they are authoritative, that they have qualified knowledge in a certain area. However, the conclusions that we draw are only going to be probable and not necessarily the case. So in this case, it's not necessarily the case that a crisis is going to occur. However, if this person has gotten it right in the past, we might want to consider acting on their opinion because they're more likely to be correct than otherwise. Causal reasoning is the last of our typical types of inductive reasoning. In causal reasoning, we are connecting cause to effect, and we can reason from cause to effect, or we can reason from effect back to cause. Here's an example of reasoning from cause to effect. You know a person who smokes, and you argue that given the fact that you smoke, it is likely that you will have serious health consequences down the road. So smoking is the cause. The health effects down the road are the effect. Now, the effect is not necessarily the case. Everybody probably knows someone who smoked their whole lives and lived a long and healthy life, but they are the exception. So even though it's not necessarily the case that smoking will damage your health, it is extremely likely. So the smoking is the cause, and the health effects are the effects of that cause. That's an example of reasoning from cause to effect. Similarly, we can reason from effect back to cause. When we do this, very often there's some event that has occurred, and we treat that as an effect, and we try to reason back to the likely causes of that effect. We do this, for example, with plane crashes, right? So the plane crash is the event, and we try to figure out, okay, what caused this event? Here's another example. When the investigators came upon the accident scene, they saw a set of skid marks about 250 feet long behind the wrecked car. A car needing that much stopping distance must have been going at least 90 miles an hour, so it is likely that speed was the cause of the accident. So here we have an effect, an event. There's a car accident. Investigators come on the scene, they try to figure out what caused the event or what caused the effect, and then they reason, well, the car was probably going too fast. Now, there might have been other factors involved. Maybe the driver was intoxicated, or maybe some obstacle appeared in the road, like a deer, for example, jumped into the road. The other things could have happened. However, given the evidence of the skid marks, that seems to indicate that the car was probably going too fast. And so we have an example of reasoning from effect back to cause. Again, the conclusion is not necessarily, but it is likely to be the case. This example is also interesting because you can see how very often when we are reasoning inductively, we're not just doing one type of thing. Here we have, of course, investigators who are presumably experts or authorities using their judgment. So we have elements of an argument from authority here. Also, these authorities are interpreting a sign. Skid marks on a road are a sign of a car stopping rapidly and perhaps going too fast, and then combining these all into a causal argument. The important point to keep in mind here is that even though this is kind of a compound example of different types of causal reasoning being combined with arguments from authority and arguments from science, the general conclusion here is that it's still a form of inductive reasoning. So to look at these different types of typical inductive arguments is somewhat artificial because in the real world we often combine forms of inductive reasoning. Nevertheless, they all share the same feature of leading to probability rather than necessity. All right, so that should give us a pretty good sense of the difference between induction and deduction, and we have some examples of inductive reasoning and deductive reasoning. So now it's time to practice. The second skill that we are trying to acquire here is the ability to distinguish inductive from deductive arguments. Our first skill we covered back in the preliminary module, which was the simple task of being able to find the conclusion of an argument, to know the different parts of an argument. Now we're acquiring our second skill, which is argument classification. Can we tell if an argument is inductive or deductive? This is crucial because it's leading up to the last and most important skill that we acquire in this first kind of unit of the class, which is argument evaluation. is the argument a good one or a bad one? Well, we won't know that, and we can't know that unless we can classify the argument properly. So this module focuses on that, learning to classify the argument properly. So in addition to this lecture and the related reading, which is also posted in the module, there are some exercises that you can go through where you're given an argument and your task is simply to determine, is it inductive or deductive? And if you can say why, that's even better. Also, I will be posting an answer key so you can check your results along the way. And then once you feel comfortable with your ability to do this, then there's a quiz in this module which covers what we've been talking about thus far during the semester. Can you find the conclusion of an argument? Can you complete an incomplete argument or an enthymeme by filling in the missing information? And finally, can you properly classify an argument? So we'll have a little quiz on those topics as well during this module. Don't try to do the quiz until you feel comfortable and have mastered the material and have done sufficient practice to confirm that you have a good sense of the material. And as always, if you have any questions, feel free to post your questions in the questions forum or email me your questions directly, and I'm happy to try to help.